actually 3x2 plus x3, I think, because I got plus 2 minus 1 is plus 1. So yeah, this is x prime prime is 3x2 plus x3 by my calculation. So check it out. We have now written this pair of second-order differential equations, right, as this set of 4 first-order differential equations. And you can do this whenever you have a system of linear differential equations of various orders. You can always play this game, introduce variables for like the first and second all the way up to n minus 1th derivatives, and you can use those to reduce the given higher order differential equations to lower order. In particular, you can always reduce it to a system of first order differential equations like this. They may not, the system's not unique, but there's a clear way to do it. Because the non-uniqueness is clear, right? Because who said x1 was y and x3 was x, right? You could have relabeled them, right? There's various other quirks of this, but let's look at this system, though. So we got x1 prime equals to x2, and x2 prime equals to minus 3x2 minus 2x3, and x3 prime equals to x4, and x4 prime equals to 3x2 plus x3. All right, so what I wanted to do was to introduce you to the matrix notation. So we could rewrite this scalar system of equations as a corresponding matrix system. And here's how we do it. x1, x2, x3, x4. The derivative of this column of functions is equal to a particular matrix times the unknown functions x1, x2, x3, and x4. So what do we put? The first one, we put 0, 1, 0, 0. That recovers this equation in the first component. The next one, we put 0, minus 3, minus 2, 0. That gets this equation. To get this x4 here, we do 0, 0, 0, 1. This one, we do 0, 3, 1, 0. So what you're looking at here, we can write more symbolically as, let's say, dr dt equals to AR, right? So this is a system of first order ODEs in, I don't know what the name of this is, but I would say standard form. I'm just my own terminology. I don't know what this, I don't remember what the official terminology is from your book. It doesn't much matter. But this is the problem that we want to learn how to solve. How do you solve dr dt equals to AR like that, where A is a coefficient of this matrix here, this 4x4 matrix is what I'm calling A. I'm calling this thing R. This is dr dt. How do we solve problems like this, right? That is the goal, right? Define x1, x2, x3, x4. Exactly. That is our goal. So the best way to do this is to use some linear algebra. All right. So we need to learn some linear algebra if we don't know it already. How many people in here have already had 221? How many people have not had 221, but have had 321? How many people who have never seen matrix algebra at all? All right, so it's harder for you guys, but it's going to be okay. All right, But keep in mind that as other people express their understanding of what I'm doing, it's because they've had a course you haven't had, right? But what I'm about to do, I mean, this is standard material in this course. It's just, it also happens to be covered by 221 and 321. In particular, what we need is the idea of an eigenvector. What's an eigenvector? What's an eigenvector? So here it is. If we have a matrix times a vector, which is non-zero, and it's equal to lambda times u again. So it's a vector non-zero, which has this peculiar property that when you take the vector and multiply a matrix by the vector, you get back the vector times some scalar multiple. Right? This is an eigenvector for A. Now, this condition is equivalent to the fact that A minus lambda times the identity matrix times u is equal to 0. So the identity matrix is a matrix that, the identity matrix would be like 1, 0, 0, 1, or if we're working 3 by 3, it's 1, 1, 1, zeros everywhere like that, etc. So that equation is the equation that an eigenvector satisfies. And the thing is, one of the theorems we have in linear algebra is this. If you have a system of equations, all right, a homogeneous system, and it has a non-zero solution, all right, then that implies that the determinant of the coefficient matrix must be 0. If this matrix was, let me look at it a different way. What would happen if the matrix A minus lambda I was invertible? What could we do? If that was an invertible matrix, what would this say? If A minus lambda I inverse exists, then what could we do? You could multiply, right? What happens when you multiply a matrix by its inverse? Let me call this thing B to give it an easier to write name. Multiply by B inverse, right? We'd have BU equal to 0, and that would say B inverse BU equals to B times B inverse times 0. B times B inverse is the identity matrix, so we have I times U equal to 0, which would then say U is equal to 0. Oops! If the inverse of B existed, if the inverse of A minus lambda I existed, that forces U to be the 0 solution. But what did we say about U at the start of all this? Non-zero, right? So it must be the case, if U is a non-trivial vector such that A minus lambda I times U is 0, it must be that this matrix is not invertible. What is the convenient way to characterize the non-invertibility of a matrix that we learn in 221 or 321? Simply this. The determinant of that matrix must be 0, right? Since we're working over the reals or the complexes, it's just that. So, in short, the determinant of A minus lambda I must be equal to 0. This is the so-called characteristic equation. For A. So, of course, we don't have time to do everything today, but I'm just going to try to do a little bit more here. We're almost done. So, if we're studying a system of differential equations, what we're going to do is we're going to look at this characteristic equation. It's going to tell us what the eigenvalues are for the matrix. All right? Then, for those eigenvalues, which are just solutions to the boxed equation, we're going to find eigenvectors. And then there is a simple way that we make solutions from eigenvectors. So check this out. If we have if R is equal to, say, e to an eigenvalue times time times an eigenvector u, then what's dr dt equal to? How do you differentiate? U is a constant vector, right? So we can just pull U outside the different. What is it, Joseph?
Is that, therefore, is that det or dev?
That's the therefore.
Oh, no, but within the box.
Oh, determinant.
Oh, determinant. Okay.
Determinant, yeah. So if I let R equal e to the lambda t times U, right? Where U is this, again, eigenvalue and eigenvector. U is constant. That means I can pull it outside of the differentiation, right? I can do this. What's the derivative of e to the lambda t? Hey, we know that. We've done that before. Lambda e to the lambda t, U, right? So this gives me what? E to the lambda t times lambda u. But u is an eigenvector, right? U is an eigenvector. So what do we know about lambda u? Lambda u is AU. So we've got e to the lambda t AU, which means we've got A times e to the lambda t times u, right? Which is what? That's A times R. So what have we just shown? Yeah, what does this boxed purple equation show about this? It shows that if you take that formula, right, and you plug it in to the differential equation, it works, right? When I differentiate it, what pops out the other side? Nothing more than A times R. That says that if you give me an eigenvalue and an eigenvector, then I can construct a solution to this differential equation using them, just like that. I call such a solution an Eigen solution. This will solve most of what we have to do. Anyway, I will actually illustrate this with matrix with a matrix with actual numbers in it, less complicated than this next time, and I'll show you how to solve some. So for those of you who don't know the matrix stuff, we're actually going to do matrix calculation next time, and it'll start to become less fuzzy. If it's fuzzy to you right now, that's okay. What you should do, if you haven't had 221 though, is you should go to your textbook and you should read like the sections on matrix math. It'll make things much less uncomfortable for you next class if you do that. Right? My notes don't have anything terribly good on that, but the book has got a nice section on matrix math that you can look at. So thanks, guys. Oh, and I've got your test.